In this lecture we talk about snake lemma. So say you're given two short exact sequences of modules. So you have the first short exact sequence, this m1 going to n1 to p1. You have these maps alpha 1 and beta 1, and then you have another short exact sequence m2, n2 and p2. You have this maps alpha 2 and beta 2. So if you're given the short exact sequences like this, and you have connecting homomorphisms f which connects m1 and m2, G is a homomorphism connecting n1 and n2, and H goes from p1 to p2. So then such a diagram would imply that there is a long exact sequence like this. So 0 to kernel of f, this kernel of this map, then to kernel of G, kernel of this map, to kernel of H, which is kernel of this map. Then you have a map delta, then you go to co-kernel of f, co-kernel of G, which is this map, and co-kernel of H. So this implies this. So this is very important because this makes a large number of proofs easy. So this snake lemma is used almost everywhere. So the correct way to see this snake lemma is like this. So you put your two short exact sequences like this. You have the first short exact sequence, and then you have this second short exact sequence, and then you construct the kernel map. So this is kernel of f, this is kernel of this map G, and this is kernel of this map H, and similarly co-kernel of f, which is m2 over image of f. So this is definition of co-kernel of f. Similarly this is co-kernel of G, and this is co-kernel of H. So we have to construct this map delta. So this map delta goes like this, and since it looks like a long exact snake, that's why we call this the snake lemma. So we have to construct this map delta to prove the snake lemma. So let us first do easy things. Let us do what we can do without worrying about this map delta. So the first thing is that we want to construct these maps, this map here and this map here. So let us just call this map as alpha 1 tilde, and we want to define this map, and this one here as beta 1 tilde. So this alpha 1 tilde is just the same map as alpha 1, but it is restricted to kernel of f. This map beta 1, again restricted to kernel of G, is beta 1 tilde. So the first thing we have to notice is that this is also a long exact sequence. So this goes to 0 and 0 comes in here. So this we have shown in previous lecture, and you again have a 0 here. So immediately first few things you have to notice is that you have injectivity right here, you have injectivity here, you have injectivity here because 0 is on the top, and similarly you have surjectivity right here. Now these two are short exact sequences, so you also have injectivity here, and you have surjectivity right here. So now we can focus on these maps alpha 1 tilde and beta 1 tilde as restriction maps. So first thing we have to say that these maps make sense. So first we will show that this map alpha 1 makes sense. So that is, if you pick some m1 here, this should get mapped to some, say, n1 here. So that is, we have to show that alpha 1 tilde of m1 is equal to some n1 which lies in kernel of G. So you have m1 here, this map is injective, so this m1 descends right here, but m1 lies in the kernel of f, so this m1 will get mapped to 0 right here. So this gets mapped to 0 right here, so this 0 will get mapped to 0 right here. This m1 now gets mapped to some n1 here. Notice that this map alpha 1 will map this m1 to n1, but now you have commutativity of the square. So you go from m1 to m2, it is 0, then you go here, you have 0. From m1 you get mapped to n1, this n1 gets mapped to 0. So that means n1 is getting mapped to 0. So if n1 is getting mapped to 0, that means n1 lies in kernel of G. So you can lift it to here n1. So this thing holds. Now similar thing we can do for the second square. So similarly, say you have this n1 here, and we have to show that this n1 will get mapped to some p1 here in kernel of h. So that is, we have to show that beta 1 tilde of n1 is equal to some p1 which lies in kernel of h. So again the same procedure, you have this injective map, so this n1 will come to n1 here, but since it is a kernel of g, it will get mapped to 0. So you have this homomorphism here, so this n1 will get mapped to some p1 right here. But this p1 will also get mapped to 0 because n1 goes to 0 and this goes to 0 right here. So n1 to 0 and 0 to 0. Now n1 to p1 and then p1 to 0. So commutativity of this square would ensure that this p1 gets mapped to 0. So that means p1 lies in the kernel of h, so you can lift p1 up right here. So this is also done. Now we want to show exactness right here at kernel of f. So you have this map alpha 1 and we considered alpha 1 tilde. Now this alpha 1 is injective because this is a short exact sequence, and this map is just a restriction map, so this map will also be injective. Now we want to show exactness at kernel of g. So you have this beta 1 tilde here. So notice again you have a short exact sequence here. So because of this short exact sequence, you immediately know that kernel of beta 1, this contains image of alpha 1. So image of alpha 1 lies in the kernel of beta 1. So this is true from this sequence right here. And this would imply that image of alpha 1 tilde, that is image of alpha 1 tilde, will lie in the kernel of beta 1 tilde. So what do we have to show? So say you have an element m1 here. This m1 you apply alpha 1 tilde to it, you get here alpha 1 tilde of m1. And then you apply beta 1 tilde to it, you get right here beta 1 tilde alpha 1 tilde m1, and this should be 0. So because you want image of alpha 1 tilde to be lying in the kernel of beta 1 tilde. So this just follows from here. You just take this m1 gets mapped here. You apply alpha 1 to it, you get alpha 1 m1 here. Then you apply beta 1 to it, you get 0 because image of alpha 1 lies in the kernel of beta 1. Now since this square commutes, you can immediately see that this will also get mapped to 0. So alpha 1 tilde m1 gets mapped to alpha 1 m1, this gets mapped to 0 because this is just a restriction map. So you can see this, and therefore this alpha 1 tilde m1 gets mapped here, so this has to get mapped to 0. Now we go in the opposite direction. So image of alpha 1 tilde contains kernel of beta 1 tilde. So this is what we have to show. So this we have shown. If we show this, then we are done. So for this we need to show this thing, that is, you start with n1 in kernel of beta 1 tilde. So you start with n1 here, which is in the kernel of beta 1 tilde, that is n1 will get mapped to 0, and then we will show that we can lift it to some m1 in kernel of f. We can lift it to some m1 right here in kernel of f, and then this m1 gets mapped to n1. So that is alpha 1 tilde of m1 is n1. So this m1 will get mapped to n1 via this map alpha 1 tilde. So we start with n1. So you picked up n1 in kernel of beta 1 tilde. Now this would imply that n lies in kernel of beta 1. So because this is just a restriction map, so if it is in kernel of beta 1 tilde, it is also in the kernel of beta 1. So that is n1 is right here. So n1 is in kernel of beta 1, but you have the sequence is exact at n1. So kernel is equal to the image. So kernel of the map going out is equal to the image of the map coming in. So kernel of beta 1 is equal to image of alpha 1. So this n1 comes from some m1 right here. So because n1 lies in kernel of beta 1, which is equal to image of alpha 1. So we are saying that n1 lifts to m1, that is n1 is equal to alpha 1 times m1. Lies in image. Precisely this, nothing much. But this n1 lies in kernel of G, so this n1 will get mapped to 0 right here. And this is an injective map, so this 0 has to come from some 0 right here. And this entire square commutes. That means m1 gets mapped to 0. So if m1 gets mapped to 0, that means it lies in the kernel of f. So m1 lies right here, and therefore we are done. So we started with n1, we went through this process, and we got an m1 which lies in the kernel of f. So again, g of n1 is 0. This implies f of m1 is 0. Since alpha 2 is injective, you picked 0 to 0, and therefore you said f of m1 is 0 because of commutativity of this square. And therefore m1 lies in kernel of f, and thus it gets mapped to n1, which we started with. So now let us construct the maps here, alpha 2 tilde and the map here beta 2 tilde. So again, these maps are induced from these maps. So in some sense these are restriction maps because they act only on part of m2 which is not modulo out by image of f. Similarly, beta 2 acts only on part of m2 which is not modulo out by beta 2 tilde. Now we have to make sure that these maps make sense. So that is, if you have some element lying in the image of f, you apply alpha 2 tilde to it, it should land in image of g, because this is just a 0 here, should also be a 0 here. And this will hold because you can start with m1 here. So if you start with m1 here, in m2 you get f of m1, and then you apply alpha 2 to it, you get alpha 2 f of m1 right here in n2. Now we have to show that this would lie within the image of g, because image of f has to lie within image of g. So this is just from the commutativity of this square. You take m1, apply alpha 1 to it, you get alpha 1 m1 here, then you apply g to it, then you get g alpha 1 m1 here, and this square is commutative, so these two elements are equal to each other. So that's what we have said here. Pick m1 and m1, and then you get alpha 2 m1 right here. This is equal to g alpha 1 m1 right here. So this implies image of f gets mapped inside image of g. So see, image of f is right here, and this lies within image of g, which is here. So g is acting on this, so this is entire thing is image of g. So therefore you can modulo out image of f and image of g. So say you have an element m2 here, you get m2 bar here after you modulo out image of f, and this m2, it is getting mapped to alpha 2 m2 right here, and this alpha 2 m2 will get descend right here. So this is what alpha 2 tilde will do. It will take image of this here and map it to alpha 2 m2, which is image of this right here. So this is what it is. So similarly, beta 2 tilde makes sense. So we have n2 here, this n2 will get mapped to beta 2 n2 here, get mapped to n2 bar here, and this beta 2 tilde will take this n2 bar to beta 2 n2 bar. Just like this map right here, you have a similar map here. Now we have to check surjectivity here. That is, we want to show that this part is co-kernel is exact. But this just follows from the surjectivity of this map beta 2 right here. Now we want to check exactness here. So we want to show exactness right here. So for exactness right here, we have to show that kernel of beta 2 tilde is equal to image of alpha 2 tilde. So first we will show this inclusion. Kernel of beta 2 tilde contains image of alpha 2 tilde, and then we will show the reverse inclusion. So we start with some n2 bar here. So this n2 bar say lies in image of alpha 2 tilde. So by definition, this n2 bar is of this form, alpha 2 of m2 bar. So that is some m2 bar here via this map alpha 2 tilde gets mapped to here, which is equal to n2. Or you have this m2 here, which gets mapped to alpha 2 m2 right here, and which gets mapped to alpha 2 m2 bar. So this is by definition. So this thing just means that n2 bar is equal to this thing. Now this n2 bar, you apply beta 2 tilde to it, it will land right here. But this entire rectangle, this big rectangle here, this entire rectangle commutes. So if you focus on m2 here, now m2 descends to m2 bar, then it goes to alpha 2 m2 complete bar, which is n2 bar, and then it goes to beta 2 n2. So this m2 gets mapped right here. Now in this direction it first goes to alpha 2 m2, then you apply beta 2 to it, so you get beta 2 alpha 2 m2. But beta 2 kills image of alpha 2, so beta 2 alpha 2 is 0 because image of alpha 2 lies in kernel of beta 2. So this gets mapped to 0 right here. So since this gets mapped to 0 right here, and you go from here to here or here to here, the diagram commutes, so this will be 0. So this is 0. So this implies beta 2 tilde n2 bar is 0. So that means that kernel of beta 2 tilde contains n2 bar. So n2 bar therefore lies in kernel of beta 2 tilde. So you started with n2 bar lying in image of alpha 2 tilde, you ended up with n2 bar lying in kernel of beta 2 tilde. Now we want to show the reverse inclusion in this direction. So you start with some n2 bar in kernel of beta 2 tilde. So you start with n2 bar right here, this gets mapped to 0. We want to show that this m2 bar lies in the image of alpha 2 tilde. So that is, there is some m2 bar here which will get mapped to n2. So more formally, you start with n2 bar here, and then you find some m2 bar such that alpha 2 tilde of m2 bar is n2 bar. So this is what we want to show. So notice that if n2 bar gets mapped to 0, that means there is some image of h in which it lies. So more formally, this n2 bar comes from n2 here, and here you have to modulo out with image of h. So this n2 has to get mapped to some h of p1 right here, where this p1 comes from here. So we are saying h of p1 is beta 2 n2. So that is, h of p1 comes from n2 after you apply this map beta 2 to it. So since beta 1 is surjective, we have beta 1 n1 is equal to p1. So you have this p1 here, this hp1 came after applying this map h, but this map is surjective because this is a short exact sequence, or you can see exactness as p1. So this p1 will get lifted here to some n1 say, and this n1 now will get mapped to gn1 right here in n2. So you apply this map g, it gets mapped to gn1. So notice that this diagram commutes. So n1 goes here and then goes here to hp1. n1 goes to gn1, and then gn1 also goes to hp1 via this map beta 2. n2 also, if you apply beta 2 to it, goes to hp1. So both n2 and gn1, they will get mapped to hp1 if you apply map beta 2 to it, just because this diagram commutes. So this implies n2 minus gn1 lies in kernel of beta 2, because if you apply beta 2 to n2, you get hp1, and again if you apply beta 2 to it, you get h of p1. Subtract them, you get 0. But kernel of beta 2 is equal to image of alpha 2. So kernel of beta 2 is equal to image of alpha 2 because of exactness at n2. This is given to you. So therefore, there is some m2 here which will get mapped to n2 minus gn1. So n2 minus gn1 lies in the kernel, and there is some m2 which gets mapped to here. Now this m2 is precisely the one which goes to m2 bar here, which gets mapped to n2 bar. So more formally, you can say there is an m2 in m2 right here, with alpha 2 m2 is equal to n2 minus gn1, just because of this. So then alpha 2 tilde of m2 bar, so alpha 2 tilde of m2 bar is equal to n2 minus gn1 bar. So by definition, so m2 bar will be bar of this just be n2 bar because you modulo out with image of g, so you kill this element right here, so you just get n2 bar. So we are done.